Lesson 4 is another application of integrals. And it's kind of a big application of integrals. I think of it as one of the bigger applications of integrals. But when we first started talking about integrals, we talked about how it is the representation of area under a curve. Okay, so when we talk integrals, we're talking about area under a curve. Well, we have done the basics of, okay, finding the area under the curve when it's the area under a curve between that and the x-axis. What we haven't talked about is the area between two curves, when your bottom boundary is not the x-axis. What do we do? And so we're looking at how to do the area just between two curves on a piece of paper. Okay? So in this lesson, we'll explore more applications of integration by investigating the area between two curves and three-dimensional volumes. Okay, volumes is not this lesson. The rest of the next several lessons are volume, because volume is another big application here. So we have two different options here for finding the area between curves. This is what I think of as our more traditional option. And this is when you have the idea of one curve on top and one curve on bottom. Okay? And this situation is going to be when your equations are solved for y in terms of x. So, your traditional, like, this is a parabola. So this is y equals negative x squared plus 2x plus 5, or whatever, random made-up numbers there. But where it's in terms of x and it's y equals. Okay? So being able to find the area in between the curves there. And we'll talk about exactly how that works here in a moment. But if you remember, when we do area under a curve, we're talking rectangles here, aren't we? And so, give me a color that's going to show up here. When we look at this, the rectangles we're looking at between these curves here are vertical rectangles. Okay? Which is what you're used to, right? When we draw our rectangles under a curve, when we've done our Riemann sums, our trapezoidal sums, we've had vertical rectangles. Now, difference over here, we don't really have a top curve and a bottom curve, do we? I mean, almost in most places, the top curve and the bottom curve are the same curve. So that makes it a little bit more difficult. I know you don't really know what we're doing yet. But so this one I think of more as a what's on the right curve and a what's on the left curve. The difference here is that these equations are not y equals and then in terms of x. These equations we're going to need to be x equals and in terms of y. Okay? With that along this lines, this also means that now instead on these, you're thinking of horizontal rectangles. Okay? Because it's going to be the rectangles are going to represent the distance between the two. Okay? So big difference is these equations here are going to be solved for x in terms of y. Okay? So solved for x and in terms of y. Whereas these over here, if you want to put the note, these are solved for y in terms of x. Okay? You don't have to. When we get there, if you want to, there is some shading we'll do, so if you want colors.
How many colors do we need to do there?
I don't know.
I see green and blue.
Yeah, I mean, there's not. And there's different shadings we can do. I think that's probably the only place that really asks you to shade, but there's various things I'll do along the way. Okay, so those are kind of your general ideas. We're going to work through this first one kind of as an investigation here. On the grid at the right, we have A through G. A asks us to graph this function. Okay, it asks us to graph f of x equals negative 1/2 x minus 2 squared plus 6. So, challenging here, because I know you guys aren't going to want to graph all those pieces. Feel free to sharpen them if you need to. What is that shape? What is f of x?
It's gonna be a parabola.
Parabola. With the vertex where?
Wait, vertex that.
Where's my vertex going to move?
2, 6. So up and to the left, right to the up. Whatever. Right to the
Up and right.
Are we agreed that the -2 takes us right 2 and the +6 takes us up 6? We're there. Okay. I can't say anything because I've been tongue-tied too. And this parabola is upside down, yes. I had several people tell me that. Okay, this has that 1/2 is the other piece we need to take into consideration. And so that means it's a compression, a shrink, not a stretch, right? Now, this is where I think of traditionally, I don't know how much you guys remember, we would have done this as far back as algebra, but traditionally in a parabola, the vertex is at 0, 0. The next set of points are at 1, 1. The next set of points are at 2, 4, and then 3, 9. Okay, what's the half do? The half cuts which values in half? The y values. So instead of going over 1, in this case down 1, it's going to be over 1, down a half.
Why did it cut the y?
Because it is a vertical compression, and so it's cutting your vertical value, it's affecting your vertical value. A horizontal stretcher compression would be on the x, which we don't see very often. Not at this level of math, at least. Okay? It's supposed to be 2, 4. So I'm still going to go over 2, but instead of going down 4, I'm going to go down 2. This is a good graphing review today, isn't it?
Mm-hmm.
Next set of points are supposed to be 3, 9. Instead of going over 3, down 9, I'm going to go over 3, 4.5. Technically, you could go another set. Because after 3, 9 would be what? 4, 16? I mean, we've got plenty of points here. But instead of 4, 16, it'd be what? 4, 8? Yeah, so even that fit. Wow. I know I didn't do that. I didn't go that far in my notes. So it's making a nice parabola, though, isn't it? I don't know. Could we do 525? It'd be.
No.
I think it'd be half below the bottom, wouldn't it? Because it'd be 12.5. So, do you have to go this far with yours? No.
It's Miss Sarkis' birthday. I'm used to it.
It really just came down to I just got going and. Okay. So I'm going to draw my parabola in. Okay. So there's my graph. Now, part B. Ask us to find the value of the integral from 0 to 5 of f of x dx, which f of x dx is the negative 1/2 x minus 2 squared plus 6 times dx. We could do this by calculator, but I think we're going to do this by hand. I promise I'm not trying to torture you. My brain is thinking this is good practice. This is good math. Okay? Now, and here's the deal. Part of the reason I'm doing this is because, on all honesty, before this year, I would have said, oh, we probably need to FOIL this out. And that's still a good option. I'm not saying it's bad. But we can also do this without FOILing it out, which is what I've seen her do in her notes some, which is what's kind of got me on the idea. It is the idea of use substitution. And I wasn't actually going to do the physical use substitution, but if we're talking use substitution, you would go in place of the x minus 2. And here's the deal with that. If that would end up being my u, well, what happens when you take the derivative of x minus 2? It's just going to be 1, right? So there's not any, what I think of as like the compensation we have to worry about. Okay, so when I integrate this, first of all, the negative 1/2 is just going to stay out front of that term, yes? And I have something raised to the second. What is the integral of something raised to the second? We're going to what? Add 1 to the power. So that 2 is going to become a 3. And we're going to divide by 3. So we're going to have a 1/3 out front, excuse me. And then because the derivative of x minus, because then if we have to think about, okay, what would have been the derivative of the inside, we can do this because the derivative of x minus 2 was just 1, right? There was nothing to compensate for. What's the integral of 6? 6x. And so this is all going to be evaluated from 0 to 5. If I clean up that front piece a little bit, it's negative 1/6 x minus 2 to the third plus 6x. Okay? Plug your values in with me. Negative 1/6 times 5 minus 2, so times 3 to the third, plus 6 times 5. And then it's minus. Do we need to plug the 0 in?
Yes.
We do here, don't we? That 0 matters on the first piece because 0 minus negative 2, or 0 minus 2 is not going to go away. 0 minus 2 is going to be negative 2 to the third. Now that 6 times 0 will go away. I agree there. Okay. So, let's see. 3 to the third is 27. I have negative 27/6 plus 30 minus negative 2 to the third is negative 8 times negative 1/6 is 8/6 if we want. So minus 8/6 and then minus 0. If this is truly a non-calculator problem and you have to finish this without a calculator, what do we need to do with 30? Actually, 8/6 and 27/6 could both reduce, couldn't they? Well,
Oh, you combine them?
Should 8/6 be negative?
Yeah.
There's the negative 1/6 times 32.
Will that be negative?
so
Lose a negative 8.
Oh no, I see.
negative. Okay.
Okay.
And then the carry.
You're making me question. I guess I should just go back here and look because I did try and think about that. So,
It's the key, no square.
yeah, there we go. Yep. Okay. So, excuse me. Yeah, 6 is the common denominator. So my brain would say this is negative 27/6 plus 30 times 6 is 186 minus 8/6. Right?
Yes. Would
I was trying to reduce, but if I reduce 8/6, it's going to be 4/3. And if I reduce 27/6, it's going to be 9/2. And so then I lose my common denominator, so. Huh? I think so. Because in my brain, negative 27 minus 8 is negative 35. And 180 minus 35 is going to be 145/6. Yes, there is a decimal equivalency. I just don't have it. So now, I guess I should have done that in blue, huh? C says shade the region in blue. What region are we shading in blue? What does that represent right there? So the integral from 0 to 5 of f of x dx.
So that area from 0 to 5 under the curve.
So officially it's not full. I guess, what do you mean by under the curve?
Like
How low does my under the curve go? To the x-axis. So when we talk about does that make sense there? Not very good shading on my behalf, but oh wait. Okay, yeah. Good. Never mind. Sorry. I glanced at my notes, which of course my notes has everything done on the graph, so I started to. Okay, so that 0 to 5 is that, it's not even that, it just goes from 0 to 5, and when we talk about that integral, it's the area under the curve, but we need to specify it's the area under the curve between the curve and the x-axis. Okay? That was C. D. We get a new function to graph. G of x equals 4 minus one half x. What is that? A line with a y-intercept at 4 and a slope of negative 1/2. Just because I can. Lots of dots. Right? Down 1, rise negative 1, run 2. Okay. That was D. Guess what E is? Nope, that's F. E, we gotta do the integral first. This time it's the integral from 0 to 5 of g of x dx. So of 4 minus 1/2 x dx. Good news is the mathing is easier here, right? I went ahead and integrated. Integral of 4 is 4x. The integral of 1/2 x, well, the integral of x is going to be 1/2 x squared times the 1/2 that's already there, makes it 1/4 x squared. Now I'm going to evaluate. I kept going. I ended up at 55/4. I plugged in my 5. 4 times 5 is 20. Minus 1/4 times 5 squared is 25/4. This time the zeros didn't matter, did they? Notice I checked though. So then I made 20 a denominator of 4, so that's 80 fourths. 80 fourths minus 25 fourths is 55 fourths. Okay. F says shade the region green. So what we're shading green is the integral from 0 to 5 of g of x dx. What is that? Where is that? G of x, of course, being this line. F of x was our parabola, yes? So what's the integral from 0 to 5 of g of x dx? Area under the curve from 0 to 5, which is area under the line here. Sorry, mine looks ugly. But it makes sense, yes? It overlaps the bottom of the other piece. Did you just describe yours as cotton candy?
It is.
Okay.
Mine kind of looks like cotton candy. Mine does not.
Mine does not. Okay. Now, the point of getting to all this. G. How would you find the area of the region that lies between the graphs? What would you subtract?
Subtract the area of x minus.
Does that make sense? We're trying to find the area between the curves. We're trying to find that piece up there, yes? If that makes sense. Okay, so yeah, how would you find that? You would subtract. I'm trying to think, yeah. The area of f of x minus g of x on the interval from 0 less than or equal to x less than or equal to 5. Now, keep this page available. Flip to the next page, because the top of the next page finishes this problem up essentially. He calls it a different problem. But number 2 says, find the area between the two curves algebraically, show your work. So we've already done the math, really. We just said we're going to subtract the area of f of x minus g of x on the interval from 0 to 5, right? So we're taking this minus this. Good news is we already have those values, don't we? Okay, we already have those values. So, in order to find the area, one thing to think about, first of all, remember your integral rules, that subtraction within an integral can be broken up to be two separate integrals being subtracted. So I can say the integral from 0 to 5 of f of x dx minus the integral from 0 to 5 of g of x dx. And we have those values already, don't we? We did all the math on the other page. (145 over 6 minus 55 over 4). If we want to really continue to treat this as a no calculator problem, as I get death stares, right? Okay. Common denominator would be 12. So multiply this one by 2, which is 290. Common denominator over here is 12. Multiply that one by 3, 165. Love it when it matches with my answer key. 290 minus 165 is, sure. Yeah, I think so. Yep. And that's how you would leave your answer if you don't have a calculator. I mean, I have it written as a decimal in my notes also. That comes out to be 10.4167, but that's what we would do there. Okay, so all of that to say, and that took a lot of time. Yikes. Okay, all of that to say, what we're trying to get you at, guys, is that notice, what did we basically do here? The integral of the upper curve minus the integral of the lower curve, right? So when you're trying to find the area between two curves, it's the integral of upper minus lower. Okay? So here, in this setup, when we have an upper and lower, I'm going to say area is going to be upper minus lower. When it's not an upper and a lower, and we think more left and right, I'm going to be more along the lines of it's going to be right minus left. Okay? What is the next problem? I have 4 minutes. Okay. She doesn't let us stop and pause and think easily here because she's already switched it into horizontal rectangles for us. Okay. So notice if we're trying to find the area of the region bounded by the graphs. So area of the region bounded by the graphs is what? That's this piece right here, isn't it? Do we have an upper minus lower we can do? That is always the upper and always the lower. And you would have an upper minus lower from here over to what, 2? But you don't have an upper minus lower here, do you? So this is where we're going to have to think right minus left. Instead of upper minus lower, we're going to think right minus left. And you'll notice the notes here. Now, first of all, WRTX and WRTY. Took me a moment to figure this out. With respect to X versus with respect to Y. Okay? Traditionally, when we go with our vertical rectangles, we're going with respect to X because we're working in terms of X. But this is what I just talked about. -1 to 2 would be good. 2 to 3 would not be good. So we're going to go with respect to Y, in case you need that. Okay. And then we can just use one integral. Now, what are my corner points here? Or what are my intersection points? Okay. This intersection point is 2, 1, correct? And this intersection point is -1, -2. Notice we need one integral for -2 to 1. What are those? The y values. Why would we be using the y values? Because we're going to be integrating with respect to y. Okay, so all things to take into consideration. Oh. You better still be here. Okay, so what we're going to set up for tomorrow, because we're doing this in respect to y. What are my y boundaries? And that is the -2 to 1, yes? Now, in respect to y, remember, we're looking at rectangles that go sideways, right? Right minus left. What's my right curve? It's x equals 3 minus y squared, so what are we going to use? The 3 minus y squared. Minus, that's my right curve, minus my left curve. What's my left curve? y plus 1. Okay? And we can just put all as one integral, that's fine. But that's where we will have to start out tomorrow. Okay? Really, we're just going to mix it up, try some different examples tomorrow, look at some different ones. I will say, the way these notes are set up, they throw us everything at once. A little different.